Okay, let's see if this works. Hello. There we go. I put a subtitle on here to make it a little bit clearer what I'm talking about here. This talk is very much geared towards stargazers. So we're going to talk about everything here is related to going out and looking up at the sky, especially going out and looking up at the sky with a telescope or binoculars, but even with the naked eye, a lot of this information is going to count. So we sit here on our planet and we look out and we can see the whole universe out there. And what that means is we're seeing things that are far away, like the planets, like Saturn, or really far away, like stars and things in our galaxy, or even more really far away, like whole other galaxies. And when we step back and look at this, I'm going to put up a scale thing here just to think about this more. We've got this increasingly pulled back scale of our planet and our solar system and the neighboring stars and our galaxy, and then all the groups of galaxies stretching out far beyond that. Out in this vast universe, most of this is empty space. Between the stars, there's very little. Most of it's a pretty good vacuum. There are gas clouds, there's diffuse material, gas and dust here and there, but for the most part, it's pretty much empty space. So when we look out at a star or another galaxy, the light from that thing is traveling from a long ways away, pretty much through vacuum. So our issue, though, is that we're standing on our planet, and our planet has an atmosphere around it. Now, the atmosphere around Earth is really pretty thin. It's not a very big thing. So this is where the title of the last trillionth comes in, because the height of our atmosphere is about a trillionth of the distance to the next star out. So you're seeing an awful lot of distance through pretty much a vacuum, and in that last little bit, the image, the light that we're seeing has to go through our Earth's atmosphere. So that's what I'm going to focus on tonight, is the effects of the Earth's atmosphere and what those effects, how they affect us as stargazers. Again, to get an idea of what we're talking about here, if you have a 12-inch globe, the thickness of our atmosphere at this scale on a 12-inch globe is about the thickness of a dime. So that's that last little bit that this nice starlight or nebula light or whatever has to go through, kind of the minefield it has to get through to get down to us for us to see it. And at this scale, I just note on here that with the 12-inch Earth, the next star would be 440,000 miles away. So again, a lot of empty space to get through this dime thickness of atmosphere. Okay, so what happens to light from these objects, these celestial objects, getting through our atmosphere? Well, our atmosphere is made up of atoms and molecules, and they absorb some of the light. So just that nature of them being atoms there filters some light, and what that affects is the thing we call transparency. So how clear is the atmosphere? Now, to our eyes, our atmosphere looks clear because we were evolved here to live under sunlight, and the visible light that we see gets through the atmosphere pretty well. Gets through the atmosphere a lot better than like ultraviolet light does or than some infrared light does, but still it does get filtered some, especially by things that are in the atmosphere besides just the air that we're breathing. So what happens by that dimming? Well, objects are dimmed. Things will look dimmer coming through to our telescopes. If there's haze, that obscures, just the haze in itself will obscure our views. And together, those make the overall performance of your telescope suffer. Your telescope things would look a lot better through it if it was on the moon or on the space station. They might not look as good looking through the helmet of your spacesuit, I suppose, trying to look through the eyepiece. But again, there is an effect of being here down on the planet. If that effect gets bad and the transparency is really poor at a given place and a given time, you might still be able to see, even on a hazy night, you might be able to see bright things like the planets or the moon through a pretty hazy night. But it may not be a good night for looking at faint things, like the little galaxy in the picture there. The haze might kill that completely, whereas, bright Jupiter will still stand out. I'm sure some of you who have observed much have looked at the moon or looked through the planets on pretty darn hazy nights, or even through some light cloud layers, and you can still see some things. But it's not a night for looking for galaxies if the transparency is poor. So the second factor that the atmosphere does is the density, and kind of the flip side of that is the temperature. It affects the density of the atmosphere is very chaotic. It's not uniform from one foot to the next or up and down in the different layers. And the changes in density cause the light coming through the air to diffract. And so the light rays coming from a star, distant star, whatever, are no longer straight. They're getting bent around. This effect causes what we call seeing. So transparency is the clarity of the air. Seeing is the stability of the air. So they're two separate things. They really aren't tied to each other weather-wise. One can be excellent, the other one poor. They can both be poor, or they can both be excellent. They're, again, not really directly tied together, but they both really affect what we see. So again, we're used to the idea of, we think about how telescopes work. You do diagrams like this, you always have these wonderful straight lines, parallel lines of light coming in from a star, a distant star, and the telescope focusing them. And you can see all the different effects of the optics. But the trouble is if these rays of light coming in, these photons of light coming in, are no longer straight lines, but bent and curved and shaking and wobbly things, your image in the end is going to suffer from that. So you get, instead of nice clear views, you can get pretty lousy views of things dancing around. And this isn't just analogous to, it's the exact same thing as looking over a hot road in the summertime and seeing heat waves. You're seeing density variations in the air, like heat waves rising, and it's bending the light rays. So those nice parallel light rays are no longer parallel anymore. They're dancing around like nuts. The row at the bottom is actually a simulation. It's a computer-generated thing of a star image and how it will dance around with seeing changes. So you could kind of make a motion picture out of that, clipping them through, and you'd see it splitting into parts and separating out. I've observed the planet Jupiter almost split completely into two images of itself and then rejoin back together. The out of focus star in the little image on the right there is actually, if you do this with a telescope and throw a star point out of focus so you get the diffraction rings of it, you can actually watch the atmosphere go past. You can actually see the cells of hotter and cooler air flowing past in front of the telescope that's causing this. So I dimmed the thing on transparency, but looking at the part about seeing, what does seeing do? Well, objects are blurred, resolution is lowered, details will come and go. You might find if you stare at a dancing around moon like that, every once in a while you get a really clear instant and you'll see the craters very nicely, and then the next instant they'll be gone again. So like this, come and go is a good term for it. But same conclusion as the section on the transparency, the overall performance of your telescope is going to suffer if the seeing is bad. So unfortunate, but true. Now, if you just have a night with bad seeing and it's clear, you might not want to look at things that you want to see details on, like the moon or the planets, but maybe it's still a decent night for looking at things that are fuzzy anyway, because they're already fuzzy. So you might still, if it's clear and the transparency is good, even if the seeing is shaky, maybe it's a good night to look at for fuzzy things, because you're not trying to see individual little craters or something on a galaxy. Okay. Now, how do we judge what the transparency and seeing are like, and how do we predict what they're going to be like? And those are two separate things. I want the really important takeaway being when I'm talking about data that we can get is that there's data of how things actually are, like whether it's raining out or not, and then there's predictions about whether it might rain or not, and those are totally different things. What's happening is what's happening. That's real data. A prediction is a prediction, and it's only worth, the paper it's written on or whatever. So that's an important takeaway. Once you look at an app on your phone, and it's got a picture of a raindrop. Does that say it's actually raining now, or they think maybe it'll sort of kind of rain? Because again, different things. Takeaway number 2, in most of these different aspects that I talk about, you'll be able to find a lot of predictions out there, weather predictions, atmosphere predictions and stuff. They oftentimes don't agree with each other, and I'll get into that a little bit more. What I have found is that I can do as good a job oftentimes for a local prediction of what the sky conditions are going to be like by looking at the data of how things are, where things are, what's moving where, what's coming, what's going. I can match or oftentimes beat what a lot of the models say, because the models are looking at different things that I am. So you shouldn't give up the idea of just figuring out yourself whether it's going to be clear tonight rather than looking at somebody's prediction. So not that I'm not going to go through a lot of prediction things too. So, but anyway, it's something to keep in mind. So now we're going to look at just transparency and how do we judge now what's real. We're looking at real data. So if it's still daytime and you want to know what the transparency is like now and maybe what it's going to be like in an hour or two when it gets dark, one of the good techniques is to look at the color of the sky. When the sun is still up and it's clear, a dark blue sky means that the air is nice and clear. There's not a lot of dust or water vapor in the air to scatter light. So that usually means you're going to have you are having good transparency at that time. The weather can always change, but as opposed to if the sky is a whitish color, even with no clouds in it, that is haze up there. So that's bad transparency, and it's telling you that in the daytime just by looking at the color of the sky. So you go out, oftentimes in this part of the country, we have our darkest blue daytime skies when we've got air coming down from Canada, where it's clearer, or the air is cleaner than it is coming from the west coast or coming from up from the south. It's oftentimes cleaner and drier coming from Canada, except when they're on fire up there nowadays. But you can recognize that nice clear Canadian air, because the sky will be a darker blue color in the daytime. So if it's a little bit later in the day and closer to your observing time, you can use this as a prediction too, though, is how much moisture is there in the air? And I'll go through online sources for looking up that data. But if the overall moisture content of the atmosphere at the various levels above you is lower, the air is more likely to be clear, more transparent, than if the moisture level is higher above you, because the water vapor does a lot to scatter light. Water molecules are bigger than the little oxygen molecules and the nitrogen molecules in the air, and so they scatter light more. So even without there being clouds present, if there's moisture in the air, you're going to get more light scattering. So now it's getting later in the day. If it's around sunset, what color is the sunset? So if the sun is going down and it's not changing color much and it's still pretty white when it hits the horizon, that generally means the air is quite clear and your transparency is good. If you have the lovely colorful sunset, or the sun turned yellow and then orange and then red going down, you have bad transparency. That's what's scattering that light, is the haze in the air, and the particulates in the air. So the sunset color can tell you a lot about how clear your air is going to be, or it is at the moment. Now, if it gets all the way to be night, you just tell by how faint stars you can see. If for your observing location you're seeing a lot of fainter stars, the transparency must be good. If you look up and you're only seeing, you don't see any clouds because it's clear out, but you're not seeing a lot of stars, your transparency is poor. So again, really affects your observing just how clear the air is, not whether there's clouds or not, but how clear the air is. If we go on to the subject of the seeing, or the turbulence in the air, if it's still daytime, there aren't as many easy keys unless you get your telescope and are looking at the sun to see what it's looking like. But there are some troublesome things in the daytime that would lead you to believe that, well, the seeing might not be very good right at the moment, and maybe it won't be this evening. If it's been a really sunny day all day long, a lot of heat can build up in the ground, in the buildings, the pavement, the trees, and everything around, and that's going to radiate out in the hours after sunset, and those are going to be heat waves rising up and creating some turbulence. If there have been any substantial weather changes, a front came through. Maybe if in the front it was cloudy all day and, oh, a front's coming through and it's going to be clear tonight. Well, great, it might be clear and it might be very transparent, but that front having come through is probably going to cause a lot of turbulence. So you might well have poorer seeing because of that. Some substantial weather or temperature swings are the same thing. If it's 80 in the daytime and you see that it's going to get down to 50 or 45 at night, that's a big drop, and you're going to have turbulence because of those temperature changes. And just high winds, either high winds at the ground, or if you happen to be under where the jet stream is coming over, which you can see from a weather map. High winds generally cause turbulence, which makes a lot of sense, I guess. So if it gets to be nighttime, the easy gauge without a telescope or an instrument of what the seeing is like is to look up at the stars and see how much they're twinkling, because star twinkling is caused entirely by the seeing, the turbulence of seeing. On a perfectly steady night with excellent seeing, the stars won't twinkle at all. And you don't often see that around here because we're in the middle of Grand Central Station here in the continent. We have weather coming from the south, from the west, and from the north, and combining and mixing and tumbling around and stuff. And so perfect seeing around here is rare, but I've seen it in other places. Don't look at the planets. They should never twinkle, although that's not exactly true. You'll hear people say, oh, the planets don't twinkle. Usually they don't, because they're not points. They're little disks, and you need to get a good twinkle on, you need to be a point source. But I've seen, on a really bad night, I've seen to the eye, I've seen Venus twinkle and change color and stuff like that. So anyway, how much of the stars twinkling, that can tell you a lot about the seeing. You'll also notice with the star twinkling, an important thing about the atmosphere in that when we look overhead, we're looking straight through that little thin dime, and it's not very much air above us. But when you look to the horizon, you're kind of looking horizontally through the dime, and you're seeing a much greater depth of air. So anything that's wrong with the air, haze or whatever that's causing bad transparency, or turbulence that's causing bad seeing, will be notably worse the closer you get to the horizon. So you might notice on some nights when you see that, like Sirius is over here, it's twinkling in the night. Let's look overhead and see whether the stars up there are twinkling as much. It's an interesting experiment, because by the horizon you're looking through more than 20 times as much air as you are if you're looking straight up, and so the effects are very much magnified. That's another pointer for if one of these conditions is bad, the seeing or the transparency, you might want to concentrate your observing more around overhead, where at least it'll be somewhat reduced effect. I guess I should have said too in the beginning, if somebody has a question about something I'm talking about at the moment, go ahead and raise your hand. All righty. Oh yeah, so what does bad seeing mean? The other way to tell the seeing is bad is everything in your telescope looks like it's underwater, like the crater on the moon that I showed you, swimming around. It's maybe not your eye, it's maybe not your telescope, it's maybe just the atmosphere that's doing the underwater thing. So, staying in the now category, looking at real references for resources, I'm going to run through some online things, and There's a ton of online resources. I'm going to run through some of the ones that I keep bookmarked and used. This is a National Weather Service site. It may not be there in a month or two. I don't know. Seriously, it may not be there in a month or two. I'm going to show you some foreign alternatives in case that happens. I like the aviation weather set that the NWS supplies because it has a lot more depth to it than the everyday common citizen, weather forecast stuff. You can see where the turbulence is. You can see where the jet stream is. You can see a lot of details more than the regular National Weather Service site has. NOAA directly sends us all the weather satellite pictures. They're not exactly live, but they're really pretty quickly updated. There's a wealth of information in the satellite images. This page scrolls way down. There's many different sets of data. All the different colors that the satellite cameras use look at different parts of the atmosphere. So I regularly look at satellite pictures. I'm going to show you a couple other resources that are good if this is too confusing about all the options. One of the things there, though, this is off of that site. This, for instance, there are 3 different bands that show the water vapor in the atmosphere. That image, the green is actual clouds. The white is probably going to look like cirrus clouds to us down here on the ground, but it'd be high, fairly clear clouds. The blue is totally clear sky, but it's very wet sky. There's a high moisture content. You get to where the yellow is there, and the water vapor content has dropped off quite a lot more. So this drier air there, this is just from Saturday. I think I downloaded this, but I've seen yellow and I've seen red pass over us here in where we live here. So you can say, wow, we're getting really dry air coming over here. That's probably going to lead, I'll hit on a couple other factors, but that's probably potentially going to lead to some really clear air that will help in my deep sky observing or whatever. But in any case, readily available all the time. These pictures are updated depending on the band. They're updated every 2 hours or every hour. Again, you can see what the weather is doing. You don't have to ask the weather guy on TV what's coming up. Getting more local, the College of DuPage has an excellent weather program and website. It's heavily with satellite pictures. They do have ones that are centered right on this area. If you want to just be able to click on a zoomed in view of Chicagoland, basically, it's handy. Again, run by the College of DuPage. This is University of Wisconsin's Space Science and Engineering Center. Another good resource for live data. If you, again, believe that the National Science Foundation is going to be around for much longer, their Center for Atmospheric Research, again, has good weather data, not only satellite, but radar and the surface maps for surface conditions and stuff too, available there. This is an independent website that just compiles from NOAA data, but the turbulence data. And if you just want to see the turbulence map, they do it for aviation, but it applies for us too, actually. And so it's easy click-on thing. If you were under this kind of magenta area here, your seeing is probably not going to be very good, even if it's clear out. So that's what that's telling. Okay, now we get from the now to that other thing, the predictions thing. And I'm going to start out with this. This is an app on my phone. It's called Windy, and it basically generates this lovely live wind map showing you what the surface winds are. But the reason I like it is it has a weather feature on it, and the reason I like that is it pulls up 7 currently 7 different models from the US and around the world that are trying to guess what the weather's going to be like for the next few days. And the thing that I do it more for amusement than for information is if you look at any given set of data, here's 3 different models out of the 7 looking at Friday, and it goes from it's either going to be completely clear to being completely cloudy or being partly cloudy. And it depends on which model you randomly pick out of that list. So it's now if they all 7 say the exact same thing, it's like that's a pretty good bet for tomorrow or for tonight or something. But sometimes you look and it's just it's raining or it's completely clear, from the 2 models next to each other. So to me, it's just kind of a learning exercise of, yeah, remember these are just models, they're just predictions, and some of them are wrong. You can just guarantee some of them are wrong. Those 3 things are not going to all happen at the same time. So anyway, looking at other things, probably at the top of the list for predictive stuff is what's shown on the clear sky charts. And we have ones for our club's locations for our observatory and for 3 of the 4 dark sites, I think, or do we have them for 4 of the dark sites now? But it's an easy to read format of what the conditions, not only the cloud cover, transparency on this is the Canadian model, which I'll get into in a little bit, but transparency also encompasses like high clouds, like cirrus clouds. But the seeing is predicted, and then there's smoke and wind and temperature and humidity if you want to look at those things down below. Probably the best things about this is the format is easy to look at and understand, but the data that it's built on are models from the Canadian Weather Service. They were actually very good. I'm not saying they're right all the time. Nobody's right all the time. But their models are built to specifically look for not whether it's raining or not, but whether it's cloudy or not. And most of the weather models that you'll see otherwise are really mostly concerned on whether it's precipitating or not, and not necessarily whether there's some clouds around. So their accuracy is reasonably good. I will show you, so this is where the data actually comes from. You can go right to Canada. Again, if all our websites disappear in the United States, there will still be the Canadian, both satellite and these forecast models. Again, very well done because their algorithms for this section, for the astronomical section, were built to try to be accurate, to talk about things that concern us, about the actual amount of cloud cover. A lot of people like their Astrospheric app or their website version of it. The base forecast information in that comes from the same Canadian model. If you pay to subscribe to Astrospheric, you can add in, I think, 4 other models that you can flip between. Again, like that windy thing with the 7 different models, there's a lot of different computers out there that are running that are trying to figure out what the weather is going to be tomorrow. The turbulence map thing actually does a forecast thing. So this is looking ahead. So if you want to see what they guess, so what's going on here, who can figure out what's going on there? That's the jet stream there. This is a polar vortex jet stream kink where this turbulence is. You get under the jet stream, you're going to have a lot of turbulence overhead, especially up at your 30,000 feet where the planes were flying and stuff. So anyway, the turbulence map does a forecast thing too. This has unfortunately become more important in the past decade or so. This is a smoke map. This is the NOAA smoke map, which I think is still listed even today as experimental. This is an old video. I picked one out from when there were a lot of fires out west, and you could see how much the fires here, here, and here were actually affecting us all the way over there in Illinois. And it was very substantial at times. So substantial enough that I smelled smoke here from Canada when it was on fire a couple of years ago. So Unfortunately, this is something that we have to add to our transparency calculations now, is what's on fire out there, because smoke, volcanic eruptions can do the same thing. A volcanic eruption can put a lot of dust in the atmosphere and spoil our transparency. So let's go on to the third factor. We did the transparency and the seeing. You've got those down. We're going to talk about this one. So those same atoms and molecules up in the atmosphere up there that were causing transparency issues also scatter light that's coming from man-made sources on the ground, scatter it across the sky and back down towards us. And that's what we call light pollution. So the reason that the sky looks bright on a clear night here, or especially it looks bright on the bottoms of clouds, is all the man-made light on the ground shining up. But on a very clear night, no clouds around, you still have a lot of light pollution here because of those molecules up there that are bouncing ground light back at us. So this is our third real big factor of what goes on in the atmosphere that affects us as stargazers. So yeah, what's going on? We should be able to look out through our atmosphere at the black universe and see black up there. But as this light starts scattering back from the ground, the sky, which seems like the background, it's really the foreground. It's kind of a weird philosophical thing to look at, but it's the transparent foreground. As it gets brighter, it'll get bright as the faint thing we want to see. So all of a sudden it's masking the faint thing we want to see. And it'll get brighter yet, and it'll get brighter than a lot of things up there. So the brighter the sky gets, if it gets to be brighter than the thing we're looking at out beyond it, that thing pretty much disappears. So that's what light pollution is. You go into the city and you look up and you see 3 dots in the sky. It's partially because your eyes aren't used to the dark. They can't get used to the dark in the city, but it's partially because the sky is so bright, it's brighter than all the fainter stars. So, and it's going to be true for your telescope too. It's going to spoil your views in major ways at times. So, and there you go. Same conclusion with the other 2 issues. The overall performance of your telescope is going to suffer if you've got a light pollution problem. So, how do we judge and predict? So again, the 2 things, the real, the now, the data, what's there, and then maybe predict what it's going to be like tomorrow or what it's going to be like at the place we're going to or something like that. So we'll look at those 2 things for light pollution, for the skyglow problem. So is this a now? No, it's actually not. This is a model. It has nothing to do with now. This is not something, well, no, we don't want to do that. Or should we wait for it to restart? Who votes for a restart? Anyway, so this is not some thing out in space looking down and saying, this is how bright your sky is. This isn't even anything in space saying how bright your sky is. So I'll go into how this model is made, but this is not a now. So how do we do nows? I'm going to stop for a moment and do a little sidetrack here, talking about light pollution and how we discuss it, or I don't want to use the word measure it. I think discuss is the better term. Traditionally, for amateur astronomers and even some professional astronomy, light pollution levels, how much light pollution there was talked about as limiting magnitude. So it's really simple. What's the faintest star that I can still see in my sky in my backyard? If it's 3rd magnitude, I can't see 4th or 5th or 6th anymore. I can see 3rd. I would say the limiting magnitude for my sky over my yard is 3rd magnitude. If it's a little darker, I can see more. Maybe I can get to 4 or 4.5 or something like that. But it's a pretty simple way to refer to how dark the sky is or how bright the sky is, unfortunately. If I want to look at it scientifically and actually be able to quantify it and also get the human eye out of the issue, I use some sort of device to measure the sky brightness. And the standard way for referring to that, for quantifying that, is in the units of magnitudes per square arc second. And that's an astronomical thing. The magnitude is the same as star magnitude, but it doesn't have to do with how faint a star you can see. Astronomers look at magnitude in an odd way. We often think of the stars being magnitudes, or heavy magnitudes, and they do, and they're point sources, so they should always look like points. But we talk about a galaxy as having a magnitude, but that galaxy, that's not a point magnitude. It's taking all the light from an area and combining it together and saying, how bright is that light if I combine that all together from that spot? Well, this is doing the same thing. This is basically saying if I take this square arc second and I take all the light coming from it and I make a point out of it, this is how bright the point would be. So it's, again, you don't have to memorize all that, but it's a way of putting a harder number on it that doesn't depend on the human eye, because you might see a different number of stars in the sky tonight going out this door than I do. So the limiting magnitude thing is a little bit more observer dependent. This is machine dependent. Going on from that, well, this guy, John Bortle, came along in 2001 and published this paper in Sky and Telescope, suggesting that his new scale that would be the way to talk about how bright or dark a sky is in a place. He said a Bortle 1 is as dark a sky as you can get, sort of, kind of, anywhere down here on the surface of the Earth. You'll be able to see everything that the human eye can see out there. And then the scale goes all the way up, getting brighter and brighter as it goes higher, all the way up to 9 is the top number, and 9 is so bright that you basically can't see any stars at all. You might see 3 stars in the sky and Jupiter and Venus or something or other. So that's downtown Chicago or whatever. So the Bortle scale is referred to a lot. This guy does all the time. He's always talking about the Bortle scale. I'm like, this is my attitude. Here's my attitude. Is the whatever. We didn't really need a new scale, but you know, it's there. So they're all talking about the same thing. It's being able to share with somebody else how bright the sky is, or to put on a table or put on a map or whatever like that. Let's talk about the limiting magnitude thing. Here's 8 charts in a row of the constellation of Orion. This little rectangle, that one, whatever. If you walked out the door and looked up at, which way am I looking? Look up at Orion over here tonight, and you only saw 2 stars. You saw Sirius and Rigel over there. That would mean you're under a magnitude 0 sky. If you toss in a few more stars, you can see Betelgeuse, and you can see Procyon. Yeah. So that's not Hyades. Oh well, that's
near
Aldebaran.
Yeah.
That is Aldebaran. Anyway, if you can see those but not these, you're under a first magnitude sky, and so on and so forth. By the time you get in the 3 stars of the belt of Orion, you're up to a second magnitude sky. Pretty simple and straightforward way of, you could walk out your door. It's probably good to get to dark adapt for a couple of minutes, but you could look up at Orion and say, gee, tonight I'm seeing, 4th magnitude stars or whatever. Actually, almost preferable to that, that's just a good example. This is the Little Dipper, which is very handy because it's in the same place all the time, which actually makes it better for comparing because it's not all the way down at the horizon and going overhead or whatever. But it's got this wonderful set of stars. Polaris is, so these are magnitudes, but there's no point. So this is 5.0. If you put a point in it, it looks like a star. So on the star map, you just don't bother with the point. We know that this is in 50th magnitude. It's 5.0. But Polaris is second magnitude. You can see Polaris, you're in second magnitude. You bop over here to the bowl of the Little Dipper. You've got second, you've got third, you've got fourth, you've got fifth. So at a pretty quick glance, if you can find Polaris and you can find any of the rest of it. So you can see Polaris, you can see this guy too. How much of this can I see? Can I see these ones in the handle that are 4.4, 4.2, 4.3? Again, any night, it's always going to be up. It's always going to be pretty much in the same spot. It's a handy, quick reference to your limiting magnitude of the sky. And it works anywhere that, until you get down to the equator, where you're not going to see it very well at all. So, okay, limiting magnitude charts. Then we're going to get into the measurement thing. This is a unihedron sky quality meter. There's one in a box up here if you want to look at it later on in person. This is a photometer for actually pointing at the sky and taking that real measurement, the eye-independent measurement. It's going to give you a number that's magnitudes per arc second squared. It's got a printout on its cute little dial right there. So they're affordable. If you're really into trying to figure out what your observing sites are like, I will get into some of the drawbacks in a minute, but this is one of them. Anything that does a measurement of something, you need to be concerned about calibration, and it's a little uncertain how long these are going to stay in good calibration. Actually, this is a paper on finding that they do shift over time, and this research group in Italy was doing prolonged research of an area, and they were watching the sky conditions slowly change over this period, and they finally realized that all their meters were slowly changing over the sky. It wasn't the sky that they were seeing, it was the meters changing over time. So something to keep in mind. Anything that's giving you an absolute quantitative measurement of something, calibration counts. Now, skipping from the now to the predictions. Now we'll go back to this map and the reasons why it's prediction. Well, how it works is satellite data is taken, weather satellite data is taken at night with images of the ground, and it sees lights on the ground, sees lights shining up in the sky. Algorithms are used to take that data and those brightness levels to estimate how much that light is going to scatter out. Whether it's not seeing the light, it's not seeing the sky glowing over Chicago, it's seeing the lights of Chicago glowing up. And the algorithms try to calculate how bright that's going to make the sky over that area. Are they perfect? They're by no means perfect, because that sky glow is affected by things that change from night to night and whatever. But they give a good estimate. This is probably the bigger issue with this data is the imagers on these satellites do not have the same color or spectral response that our eyes do. So they see lights and sky glow a lot differently than we do. There was some effort made in the algorithms to change that, but they really are limited at it. The biggest issue is that for doing the weather work that these cameras are made for looking at clouds over the land at nighttime, they do not see blue light at all. And unfortunately, with the switch from the yellowish high-pressure sodium streetlights that we used to have to the white LED lights, we've ramped up the blue output at night tremendously, and these cameras didn't see that change at all because they don't see that additional blue light. So these models are not responding well to that switch to blue light. Also, sky glow is caused more by blue light because it scatters more, and also because our eyes are more sensitive to it in our nighttime vision. So we see the sky as being brighter if it's lit up in blue than if it's lit up in yellow or red or whatever. And then the spatial resolution is not particularly fine. Again, the algorithm tries to guesstimate over wider areas. So the area here might be more affected by this light than it shows, or less than it is than it shows. It's really hard for a model like this to figure these things out. So caveats on that. Not that this doesn't give you some indication of reality. It probably still would be good if you lived over here to try to head to that area there. It probably is darker, but it may not give you the numbers that this map does. This map is a guess. It's a prediction. Yeah, and there we go. Light pollution levels are not static. It shows a certain amount of light pollution over where we are in this map now. It's showing a little red there. That light pollution level over here varies a lot. There's snow on the ground. Boy, is there a lot more light pollution here. It's reflecting the ground light back up in the sky tremendously more. So your sky quality changes substantially with things like that. Okay, complications. So I probably touched on some of these already. Again, really important. The atoms and molecules up there doing anything, this stuff changes all the time. I've watched the light pollution level on a clear night change substantially, just with me being out there underneath it watching it. This is an example of that. This is readings taken, this is over 1,000 readings taken with an SQM, a unihedron meter in one location in Arizona. Each little yellow mark is a reading. The highlighted spots are an algorithm looked at that data, tried to pick out where there were almost certainly no clouds and no moon, and find the lowest brightness, or in other words, the darkest sky reading, and it marked those off. So this is all the same location. The scale going across is the sidereal time in the location. So what it is what part of the sky is going over. So these are all nighttime readings. There's no daytime here. The reason there are two humps in it is because the two sides of the Milky Way going over. So there aren't any, your sky is at its darkest here. The algorithm never said, oh, the sky is at its darkest here because the Milky Way was going over. But again, every one of these dots is the lowest reading in a one bank of data that the algorithm found, all for the same spot. And you can see there's quite a bit of variation. So you can't say this spot in Arizona has a sky brightness of 22.0 or 22.4. It has the sky brightness of a lot of different things, depending on what the atmospheric conditions are like. This is another look at the same kind of data. This is at Lowell Observatory in Flagstaff on Mars Hill. So this is a bunch of points like that. Again, these are the darkest readings taken out of data sets there in pretty much constant live monitoring. And this is plotted by the time of night. And so you see, again, same location and the darkest readings taken through different sessions. The sky brightness actually changed quite a bit. But there's an interesting thing here in looking at the night is the brighter sky is going this way, the darker sky is toward the top. You go through the night and this actually slopes up a little bit here because the sky gets darker on average through the night. And it's not uncommon. I think in Flagstaff, to me, it's pretty clearly, having spent quite a bit of time there, not related to parking lots turning off their lights. They don't turn off any street lights. There are fewer cars on the road. Down there, the highway traffic, especially nowadays, with our especially nice new bright headlights, actually contributes a lot to the sky glow. So there's fewer cars on the road here in the wee morning hours than there are in the evening hours, so the sky gets darker. So again, just through an average night, the sky brightness can change. Is this all making any sense up to this point? Are we doing good? Okay, now we'll get to how to deal with these issues. And I'm going to try to not just resort to platitudes, but I'm going to put up a number of different points. I usually don't put up big read things, but you get to read these along. So this is an important one. You get a new telescope or an old telescope or whatever. Don't judge how good it is with one session of looking through it. You may have a perfect telescope and you brought it out on the worst night of the year, and nothing's ever going to look good on the worst night of the year. Same thing for the observing site. Don't be surprised if you go to someplace like one of our club's dark sites, and the first night you're there, it's amazing and wonderful, and you can see a bunch of things you've never seen that well before. And you go another time, you're like, what's going on here? You know, am I getting cataracts or something earlier because I'm not seeing what I saw the last time? It looks like it's clear out, but maybe you've got issues with the light pollution or the transparency or the seeing. This is the other way around. Only expect to see really great nights with both transparency, but especially seeing here, on rare occasions. There's probably 4 good nights a year, exceptional nights a year here. Some years there may not be any, where things are just top notch all the way across. There are other places in the world that are better than this, places where you're higher in the air, where it's 630 feet probably here in this church, something like that above sea level. If you get 10,000 feet above sea level, there's a lot less air to look through, obviously. If you get farther away from 8 million people than we are here, it might well get darker and stuff too. But enjoy when you get the exceptional, the exceptional night, enjoy it. Learn to adapt your target list. And again, I pointed this out before. Seeing, looks clear, you get your telescope up, the seeing turns out to be crappy and everything's really blurry. Look for fuzzy things. Look for things that doesn't matter if they're a little blurred. Don't try to split double stars or find new half-mile wide craters on the moon or whatever like that. If it's a hazy night, sometimes hazy nights have the more stable air, and maybe the seeing will be better, and that's the time to split double stars or look for festoons in the clouds of Jupiter or whatever like that. So adapt for what chaos presents to you. And again, do realize that poor performance may not mean that something went wrong with your eyes or with your telescope or something or other. You're probably not imagining it. Like, I could have sworn I saw more when I looked at this the last time. Well, you probably did, and you probably will the next time you look at it. It's not necessarily. Not that things don't go wrong with telescopes or eyes. Realize that these things affect daytime observing too. If you observe the sun, seeing and transparency are definitely going to be factors there too. They will affect what you see. If you observe the sun in hydrogen alpha, and I don't know if any of you do, hydrogen alpha is very sensitive to transparency, and it may look clear out, and the sun looks reasonably white and not all yellow or whatever, but what you can see in details of solar prominences and things is very much affected by transparency. So a little bit of haze can really be deleterious to that. Understand that other turbulence that causes bad seeing can happen anywhere, the turbulence itself. This is why we take our telescopes out and let them cool off before we start observing on a night like this when it's in the single digits out. If you bring it outside, it's at 68 degrees and you set it in your yard, it's going to be radiating like nuts. There's going to be heat waves rolling off of it for the next couple of hours. And right in front of the lens, or in front of the mirror, or whatever it's made of, you're going to hit heat waves rolling off of it that'll spoil your view. Somebody standing in front of your telescope, I've seen this happen, and in cold weather, just the heat coming off of somebody's head, you can watch your image go away in your telescope. Over the neighbor's house, if it's been sunny all day and their roof got hot, the heat rising off their house can really affect your seeing. Most bad seeing turbulence is within a couple thousand feet of the telescope, because if you're looking up, you get above a couple thousand feet and the air is already starting to get a little bit thinner, and there oftentimes isn't as much big turbulence there. It's just smaller turbulence up higher. Anyway, so it's something to keep in mind of where is turbulence coming from. And don't let your friends stand in front of your telescope while you're looking there. They can stand over here. It makes a difference. In cold weather, it makes a difference. When it comes to light pollution, so this to me is important too. It's an adaptation thing. In Naperville, I don't think there's probably any place in the city limits of Naperville that has better than a 4-point-something magnitude sky. But where you're actually looking from, whether you're looking with your eyes or your binoculars or your telescope, it makes a big difference. If there's lights that you can directly see, they're really going to be affecting your viewing more than the sky glow is going to. So if you get a locally dark spot, that can make a big difference. So, again, as I pointed this out, don't rely on the maps, because they're not really maps, they're models. And the way to get a good measurement of the light pollution effects in a given spot are to go there and look. And has been part of the team that did all of the searching for our dark sites that we have. we know that there are places that looked really good on the map, but all you need is one barn light that's on all night long, and that's so much for that, you know. So, do remember, as I've been drilling into you, that the light pollution levels can change dramatically over a given spot over time, as easily as the weather. Okay, and I do have to touch on this because people will ask about what about filters. So really quickly, my biggest answer is that I gave a program that's on our YouTube channel, and it's still there on filters, and it goes into this subject in quite a bit of detail. So look it up on the YouTube, and if you really want to know. But in really quick summary, the Lumicon came out with the nebular filter in the early 1980s. We actually have 2 of these from that era out at the observatory. Back then, what you needed to do to be darkening the sky so you could see nebulas and things more, most of the sky brightness was from high pressure sodium lights. And this is the spectrum coming off of a high pressure sodium light. It's mostly this peak of yellow and orange and red. And so the rest of the whole bandwidth visible there is pretty open. So mainly what a filter like this needed to do was block out that yellow, orange, and red. And that's what these wider band older filters did. Now we have white LEDs, and their spectrum output looks like this. It's no longer focused in a spot. It's gosh darn everywhere. And so this is a 4K, 4KK, 4,000 Kelvin white LED, and that's very common for outdoor lights now. So what we need to do to have any hope of filtering anything there is to go the other way around and have the filter. This is a Botter Planetarium's rating for one of their own narrowband filters. All it lets through is tiny little slivers of light where there's an emission line for triply ionized oxygen and the emission lines for hydrogen over here. And it blocks out everything else with an attempt to try to get rid of more of that stuff. Unfortunately, gosh, this is still in a really bright area, and this is still in a really bright area. So the filters are not going to solve light pollution. The big limitation is they only will work on narrowband emission nebulas. It's not going to help you with a galaxy. It's not going to help you with stars, things that emit all across. It's only letting through these 2 little slits of light, and things that emit all the way across the spectrum, like stars and galaxies and whatever. There you go. I have found, like I know a number of people have, they actually are the most help in a place that's already somewhat dark. You might find better results with a light pollution filter out at with a narrowband filter out at one of the club's dark sites, out at Caton Farm or Ransom Road or Manuka, than you do in your own backyard, because that little bit of difference darkening the sky up can make a big contrast difference for you. It's not going to eat its way through the skyglow of Chicago very well. So that's this kind of a nutshell there. So conclusion there, adapt. I say enjoy trips to places with darker skies, better seeing, or more clear nights, but don't give up in observing from around home too. Just adapt to what you can still effectively do. Even if you live in downtown Chicago, there's still observing you can do, as Ron has told us a number of times. And so that's what I had put together. And I assume that there's going to be people who either have questions or want to comment on some of all the stuff that I've said.